Alright, let's go. Number 10. The Vanishing WIMP. In 1977, Benjamin Lee and Steven Weinberg were not looking for dark matter. They were calculating a cosmological bound on how heavy a neutrino could be without overclosing the universe, a routine relic abundance problem. Their paper appeared in Physical Review letters that year, and buried inside it was an accident. The accident was this. Take a particle with a mass near the weak scale, roughly 100 times the proton, and give it ordinary weak force interactions. Run the early universe forward. As the plasma cools, that particle stops annihilating and freezes out, and the leftover density comes out almost exactly equal to the dark matter density we observe. Nobody put that in by hand. Physicists called it the WIMP miracle, and it defined the next 40 years of experimental effort. If the miracle is real, those particles are streaming through the Earth right now, and one of them should occasionally strike a xenon nucleus hard enough to make it flash. We built the detectors. Every one of them is empty. The LZ experiment sits nearly a mile underground at the Sanford Underground Research Facility in South Dakota. 7 tons of liquid xenon, 250 scientists, 37 institutions. In their 2024 result in Physical Review letters, drawn from 4.2 ton years of exposure across 280 live days, the collaboration reported no excess over background. Their strongest exclusion sits at 2.2 times 10 to the minus 48 square centimeters at a mass of 40 giga-electron volts. Scott Kravitz at the University of Texas at Austin put it plainly, they have dug roughly 5 times deeper than anyone ever had before. Every escape route has been walked down. Maybe the particle is heavier than expected. But the Large Hadron Collider has excluded the supersymmetric partners that motivated it out past 2 tera-electron volts. Maybe it is lighter. LZ has now pushed below 9 giga-electron volts and found nothing there either. Maybe the interaction is weaker still, except LZ has just detected boron-8 solar neutrinos scattering off xenon, which means the experiment has reached the neutrino fog. The irreducible floor where solar neutrinos mimic the signal itself. Maybe the coupling is spin-dependent rather than spin-independent constrained. Maybe the halo model is wrong, but every reasonable variation has been tried. If the standard picture holds, a few 100 million dark matter particles are passing through your chest every second, and have been every second of your life. Nothing in you has ever registered one. Nothing anyone has built has either. At what point does a null result stop being a measurement and start being an answer? The candidate that failed first was the least exotic one. Number 9. The empty halo. In 1986, Bohdan Paczynski at Princeton published a paper in the Astrophysical Journal proposing something almost mundane. He was working on gravitational lensing statistics, and he noticed that if the galactic halo were full of dark, compact objects, dead stars, rogue planets, stellar black holes, then one of them would occasionally drift across the line of sight to a background star and briefly magnify it. Not a rare cosmic event. A measurable, repeatable one. The prediction was clean. Monitor several million stars in the Large Magellanic Cloud. If the halo is made of half solar mass objects, you get a specific number of brightening events per year, with a specific achromatic light curve shape. Count them, and you weigh the dark halo directly. 2 teams did it. The numbers came back wrong in both directions. The MACHO collaboration, reporting in the Astrophysical Journal in 2000 under Charles Alcock, monitored 11.9 million stars for 5.7 years and found somewhere between 13 and 17 events, enough for about 20% of the halo, not 100. Then the EROS 2 collaboration. Patrick Tisserand and colleagues. Published in Astronomy and Astrophysics in 2007, 33 million stars, 6.7 years, and after restricting to bright, unambiguous sources, an upper limit under 8% of the halo across masses from a 10 millionth of the Sun up to 15 solar masses. Each proposed constituent died separately. Brown dwarfs and faint stars fail because Big Bang nucleosynthesis caps all baryonic matter at roughly 5% of the critical density. There simply are not enough protons and neutrons in the universe to do the job. White dwarfs fail because a population that large would have flooded the halo with carbon and nitrogen we do not see. Neutron stars and stellar black holes fail because their progenitors would have left a chemical signature across the Milky Way. And the handful of MACHO events that were seen are now widely suspected to be stars in the Magellanic Clouds lensing other stars in the Magellanic Clouds, the halo contributing nothing at all. Whatever holds the galaxy together is not rock. It is not iron. It is not a dead sun. It is not made of anything you have ever touched, or could ever touch. If it is not matter as we have ever encountered matter, what exactly are we counting when we weigh a galaxy? The next candidate was invented to solve a completely different problem. Number 8. The silent cavity. In 1977, Roberto Pecci and Helen Quinn at Stanford were trying to fix an embarrassment in the strong nuclear force. The theory permits the neutron to have an electric dipole moment. Experiment says it does not, to better than 1 part in 10 billion of the natural expectation. Pecci and Quinn proposed a new symmetry to force that number to 0. They were not thinking about cosmology at all. Then Steven Weinberg and Frank Wilczek, independently, both in 1978, both in Physical Review letters, pointed out what their symmetry required. Break it, and you get a new particle, extraordinarily light, extraordinarily weakly coupled. Wilczek named it the Axion. The consequence arrived later. A particle that light produced non-thermally in the early universe behaves exactly like cold dark matter. And in 1983, Pierre Sakivi showed in Physical Review letters how to catch one. Inside a powerful magnetic field, an axion can convert into a single microwave photon. Build a tunable resonant cavity inside a large magnet, sweep the frequency, and listen. They have been listening for 30 years. The cavity is still quiet. A DMX, the Axion dark matter experiment, runs a copper cavity roughly 60 centimeters across and a meter long inside an 8 Tesla superconducting magnet, cooled by a dilution refrigerator to around 150 millikelvin. The expected signal power is about 10 to the minus 23 watts, on the order of 100 photons per second. In 2016, it became the first haloscope to reach the pessimistic Defaseur coupling, excluding axions between 2.66 and 2.81 microelectron volts. Later runs extended that to 3.31. The most recent result, published in Physical Review letters in March 2025, covers 3.27 to 3.34 microelectron volts. Add it up. After 3 decades, the excluded band is well under 1 microelectron volt wide. The theoretically plausible range spans roughly 1 to 1,000. Every acceleration strategy has stalled. Scan faster, and sensitivity drops as the square root of time. Go to higher masses, and the required cavity volume collapses with the cube of the frequency, so the signal disappears with it. Use arrays of small cavities, and phase matching becomes a nightmare. Build dielectric haloscopes instead, proposed, funded in part, not yet delivering. Astrophysical bounds from supernova 1987A squeeze the range from above, and string theory constructions suggest not one axion, but an axiverse, a spectrum of them spread across dozens of decades in mass. The instrument may be working perfectly. It may be tuned to the wrong station, and it may stay there past the end of everyone currently operating it. How do you falsify a particle whose mass is allowed to be almost anything? The problem is not only what dark matter is made of, but how it behaves when it collides. Number 7. The cluster that disagreed. In the early 2000s, Douglas Clow, Maru Abrata and their collaborators were doing something unremarkable, building weak gravitational lensing mass maps of merging galaxy clusters, measuring where the mass sits. It was the kind of survey work that fills a career quietly. The prediction under test was simple and sharp. In a cluster collision, the hot gas, which carries most of the ordinary mass, slams into itself, shocks, and slows down. The galaxies, being small and widely separated, sail through untouched. If dark matter is collisionless, it must sail through with the galaxies. If it interacts with itself at all, it should lag behind. In the bullet cluster, it sailed through cleanly. The lensing mass and the X-ray gas were separated at 8 sigma. That result, published by Clough and colleagues in the Astrophysical Journal Letters in 2006 under the title A Direct Empirical Proof of the Existence of Dark Matter, became the single most cited piece of evidence in the field. It is also where the trouble starts, because other clusters refuse to repeat it. Abell 520, nicknamed the Trainwreck, was reported by Andisha Madhavi and colleagues in 2007 to contain a dark core sitting with the gas, with almost no galaxies attached, and a mass-to-light ratio near 800. Myungkook James G. and colleagues reobserved it with deeper Hubble data in 2012, and the core survived. Then Richard Massey and colleagues, in monthly notices in 2015, reported that in Abell 3827 the dark matter of one central galaxy was displaced from its stars by 1.62 kiloparsecs, implying a self-interaction cross-section around 1.7 times 10 to the minus 4 square centimeters per gram. Each anomaly then eroded. Massey's own team returned to Abell 3827 with ALMA and the Velt's Muse spectrograph and published in 2018 that the offset was gone. Better foreground subtraction, better image identification, no displacement. Abell 520's dark core has been attributed to projection along the line of sight, though G's deeper imaging did not dissolve it. Statistical work across 72 cluster collisions by David Harvey and colleagues in Science in 2015 found the dark mass tracking the galaxies to within 5.8 plus or minus 8.2 kiloparsecs, a cross-section under 0.4 7 square centimeters per gram, entirely consistent with zero. The strongest empirical proof that dark matter exists rests on one collision. A nearly identical collision 40 years of telescope time later still cannot be made to agree with it. If the evidence only works in the systems we chose to trust, what is the evidence actually measuring? Some candidates escaped every constraint by hiding in a window we cannot look into. Number 6. The window that cannot close. Stephen Hawking was not proposing a dark matter candidate. In 1971, publishing in monthly notices of the Royal Astronomical Society, he was working through what happens to density fluctuations in the very early universe, a technical question about gravitational collapse in a radiation-dominated cosmos. Yakov Zeldovich and Igor Novikov had raised something similar in 1967. Hawking's conclusion was that any region dense enough would collapse directly into a black hole before a single star existed. That gives you an object with a decisive advantage. Because primordial black holes form before nucleosynthesis, they do not count against the baryon budget. Every constraint that killed brown dwarfs and dead stars simply does not apply. Dark matter could be black holes, and none of the chemistry would notice. In 2015, LIGO detected merging black holes around 30 solar masses, heavier than expected from ordinary stellar evolution. Simeon Bird and colleagues at Johns Hopkins published in Physical Review Letters in 2016, arguing these could be primordial. The field reopened. Then the mass windows shut, one by one. Below about 10 to the 15 grams, Hawking evaporation means they would already be gone. The stellar mass range is closed by the same Eros and Ogle microlensing surveys that killed the MACHOs, and by Planck constraints on accretion heating the early universe. And the intermediate range fell to a single night of observing. Hiroko Niyakura, Masahiro Takada, and colleagues pointed the Subaru Hypersuprime cam at Andromeda on the 23rd of November 2014, took a 7-hour exposure at a 2-minute cadence, covering tens of millions of stars, and found exactly one candidate event where hundreds were expected. Published in Nature Astronomy in 2019, it excluded primordial black holes as the bulk of dark matter from about 10 to the minus 11 up to 10 to the minus 6 solar masses. One window survives, asteroid masses, roughly 10 to the 17 through 10 to the 23 grams. It survives for an uncomfortable reason. At those masses, the black hole's Schwarzschild radius approaches the wavelength of visible light, wave optics takes over, and the microlensing magnification smears out. The window is open precisely because the method that closed all the others goes blind there. Dark matter may be a fog of objects, each weighing as much as a mountain, roughly 1 per volume of the solar system, drifting through the galaxy and through you. What does it mean to have a candidate that fits every observation and can never, even in principle, be seen? There has been exactly one claimed direct detection of a dark matter particle, and it came from an instrument aimed at something else. Number 5. The line at 3.5. Esra Bulbul, then at the Harvard-Smithsonian Center for Astrophysics, was studying the hot intracluster gas in galaxy clusters. The work is spectroscopic bookkeeping, stack X-ray observations, model the continuum, identify the emission lines from iron, silicon, sulfur, potassium, and extract abundances. It is careful, unglamorous, and every line in the spectrum is supposed to have a name. In the stacked spectrum, one line did not. It sat at 3.55 kilo-electron volts, and no known atomic transition explained it. Bulbul and colleagues published in the Astrophysical Journal in 2014, stacking 73 clusters from XMM Newton's MOS and PN cameras, detecting the feature at 4 to 5 sigma. Alexei Boyarsky and colleagues, in Physical Review Letters the same year, independently found it in Perseus and in Andromeda. The natural interpretation was a sterile neutrino of about 7.1 kilo-electron volts decaying into a photon in an ordinary neutrino, with a mixing angle around 7 times 10 to the minus 11. Then the dismantling began. Potassium-18 has transitions at 3.47 and 3.5 1 kilo-electron volts, and at the roughly 100 electron volt resolution of a CCD, they are not cleanly separable. The entire signal is a 1% bump on a continuum. Tayuki Tamura and colleagues found nothing in Suzaku data on the same cluster. Michael Anderson and colleagues in 2015 found no line in stacked galaxies, which under a decaying dark matter hypothesis is directly inconsistent since flux must scale with projected dark matter mass. The instrument built to settle it was Hitomi, launched in February 2016 with a 5-electron volt microcalorimeter, sharp enough to resolve the line from the potassium. It observed Perseus, saw no line at the claimed flux, and then broke apart in orbit a month into its mission. Its successor, X-RISM, has since stacked 3.75 megaseconds across 10 clusters and found nothing, with an upper limit 3 to 4 times below Hitomi's, still 5 times above what Bulbul reported. The most direct evidence anyone has ever offered for a dark matter particle is a faint excess in an X-ray spectrum, and the one machine capable of confirming or killing it was destroyed before it could finish looking. If a signal cannot be reproduced and cannot be explained away, what is it? Some physicists concluded the particle was never the problem. Number 4. The constant that should not exist. Mordechai Milgrom was on sabbatical at the Institute for Advanced Study around 1980, working through galaxy rotation curve data. The known anomaly was that rotation speeds stay flat far outside the visible disk instead of falling off. Milgrom asked a narrower question than everyone else, not how much mass is missing, but where exactly the discrepancy switches on. It does not switch on at a fixed radius. It does not switch on at a fixed density. It switches on below a fixed acceleration. Milgrom published 3 consecutive papers in the Astrophysical Journal in 1983, volume 270, pages 365, 371, and 384. Modify Newton's second law below an acceleration of about 1.2 times 10 to the minus 10 meters per second squared, and the rotation curves follow, with one universal constant and no per-galaxy dark halo to fit. In 2016, Stacy McGaugh, Federico Lelli, and James Schoenbert published the radial acceleration relation in Physical Review Letters 153 galaxies. Thousands of data points, spanning dwarfs to giants, and the observed acceleration is predicted by the visible matter alone, with a scatter of roughly 1/10 of a decade. Then every attempt to make it a real theory broke. It had no relativistic formulation at all until Jacob Bekenstein published Teves in Physical Review D in 2004. On the 17th of August 2017, the neutron-star merger GW170817 arrived with its gamma-ray burst 1.74 seconds later, after traveling roughly 130 million light-years, pitting the speed of gravity to the speed of light at the level of 1 part in 10 to the 15, and killing Thebes and most of its relatives outright. Milgram's law also fails in galaxy clusters, where it still leaves roughly a factor of 2 of missing mass. It has no natural account of the third acoustic peak in the cosmic microwave background, and the bullet cluster puts the lensing mass where the baryons are not. The theory that cannot possibly be right keeps making successful predictions on precisely the scale where we live, orbit. And look up. The theory that works everywhere else cannot explain why. Why should a galaxy care about a number with the units of acceleration? The most persistent anomaly in the field is not a theory at all. It is a single detector that will not stop reporting. Number 3. The wind only one detector feels. In 1986, Andrzej Drukier, Catherine Fries and David Spergel were working out how anyone might actually detect a galactic dark matter particle, publishing in Physical Review D. Their insight was geometric, not exotic. The sun plows through the halo at roughly 220 kilometers per second towards Cygnus. The Earth orbits the sun at about 30, on a plane tilted around 60 degrees to that motion. Half the year the Earth's velocity adds to the sun's, half the year it subtracts. That means the apparent dark matter wind should get stronger and weaker on a strict annual cycle, peaking around the 2nd of June, with an amplitude of a few percent. No particle physics assumptions required, just orbital mechanics. One experiment has been reporting exactly that signal for a quarter of a century. No other experiment has ever reproduced it. Dama/Libra, led by Rita Bernabe at the Gran Sasso National Laboratory in Italy, runs about 250 kilograms of ultra-pure sodium iodide. Their full exposure now stands at 2.86 ton-years across 22 annual cycles, with the modulation reported at 13.7 sigma. The measured amplitude is 0.01014 plus or minus 0.0007 4 counts per day per kilogram per kilo electron volt. The measured phase is 142.4 plus or minus 4.2 days. The predicted phase is day 152.5. The period comes out at 0.99834 years. Everyone has tried to break it. Muon flux modulates seasonally underground, but the phase does not match well enough. Neutron backgrounds, radon, temperature drift in the photomultipliers, seasonal groundwater, each proposed, each examined, none sufficient. The only decisive test was replication with the same target material. And it has now been run twice. Cosine 100 at Yongyang in Korea released its full 6.4-year dataset, disfavoring the Dama modulation at 3.57 sigma, and Anais 112 at Canfranc in Spain reported 6 years of data incompatible at 4 sigma. Neither has reached the 5 sigma threshold that would formally close it. For 25 years, a detector under an Italian mountain has been reporting that something blows through it every June. Nobody can find the particle. Nobody can find the mistake either. How many independent null results does it take to overturn one signal that refuses to go away? The failures are not confined to detectors. They appear inside the simulations themselves. Number 2. The satellites that never came. Anatoly Klypin, Andrei Kravtsov, Octavio Valenzuela, and Francisco Prada were doing a consistency check, running high-resolution N-body simulations of a Milky Way-sized halo in cold dark matter, then counting what came out to confirm that hierarchical structure formation reproduces the galaxy we live in. Nobody expected a crisis from a head count. The theory's central claim is that structure builds from the bottom up. Small halos form first, merge into larger ones, and their dense cores survive the merger as substructure. That substructure is not a side effect. It is the mechanism. The simulation produced roughly 500 surviving subhalos above the circular velocity of Draco and Ursa Minor. The Milky Way had 11 known satellites. Klypin and colleagues published in the Astrophysical Journal in 1999, volume 522, page 82. Ben Moore, Sebastiano Gigna, Fabio Governado, and colleagues published the same discrepancy in the Astrophysical Journal letters that year, volume 524, and put the mismatch at a factor of about 50.